Okay, so the next point I wanted to discuss is, as I said before, the equation of motion for a particle moving in whatever metric I'm looking at. I haven't specified the metric at all yet, but once I have the metric, let's try and see what kind of equation of motion I should get. So let's just remind ourselves, right, in Newtonian theory, my equation of motion is Newton's second law. It's very simple. It's just given by whatever external force I apply to the particle divided by its mass. So that gives me the acceleration of that particle, and then I can integrate that forwards in time, right? And then I can find this as a function of time. So I know where the particle is at all times in the future, and I can do this for all particles. And it just assumes that I can calculate the force, right? So it could be gravity or it could be any other force that I'm looking at. So what does something like this look like in both special relativity and in general relativity? So let's just start by special relativity. So in special relativity, whatever equation I'm looking for must be something related to the 4 vector, right? So I must include time, and then whatever I should put here, that's a little bit unclear. Let's assume that we're looking at a particle with a mass. So of course that particle has some proper time, right? Because whatever it does, I can always be at rest in the frame of the particle, and then I can do my time derivative there. So I could always make this differentiation with respect to proper time. And that should be equivalent to something. Now remember, in special relativity, there's no gravity, right? So if I don't look at electromagnetic forces or whatever, then somehow, somewhere on the right-hand side, there should be a 0. But it's not exactly clear that this is actually the correct equation. One would need to look a little bit further in order to establish whether that's the correct equation. And there's a variety of different ways of doing that. And in the notes I put on Blackboard, I describe just one way, and that is to use the variational principle. So the variational principle you've seen in other types of courses, it always has to do with calculating what is known as an action. And that action always appears as an integral over some path taken by the system. And normally in classical mechanics, what I do is I actually integrate over the Lagrangian. So I take a system from some configuration A to some other configuration B along some trajectory, whatever that trajectory is. That trajectory can be calculated using this so-called variational principle. What it says is just that the physical path must correspond to an extremum point of the action. So it must always fulfill ds equal to 0. And then I do variation on this integral here, and then I can, in normal classical physics, I can find the Euler-Lagrange equation based on the normal Lagrangian, which is kinetic minus potential energy, right? So that's a completely standard way of doing this, and you've seen it in analytic mechanics, for example. Now you can also do other things. For example, you can formulate Fermat's principle in terms of this variational principle. We know that the actual path taken by a photon or a ray of light is always an extremum of the path length, right? So it's just saying that photons always move in straight lines, basically, depending, of course, on what kind of medium I'm looking at and so on. But you can do that the same way. And in special relativity, you can again apply the variational principle. It's just not the normal Lagrangian of classical mechanics we're using. It's some kind of other Lagrangian or action that we want to calculate. And actually, the equation of motion in special relativity can be formulated by saying that I always want the total time or total proper time, which is given by this, to be an extremum. So I want to take a physical path taken by a particle, and then the postulate is that I need to do variations and I need to find the extremum point of this. And that you can do. I won't bore you with the details. They're in the notes if you want to actually check out how it goes. But what you find is that if you apply this, well then, okay, in here, the point, let me just sketch it. The point is, we know here that d tau is equal to squared is equal to minus ds squared. That's what we established before, right? And that means I can write d tau as square root of minus ds squared. Remember, d tau is a positive definite quantity, so it has to look like this, and that means that I can write tau as the integral over this quantity here. So I need to integrate this along the line of sight, and then I need to do variations. And I can further write this out as minus g mu nu like this. And then it would be true even in a more general metric than the one in special relativity. But it's certainly true in special relativity. And then I can apply the variational principle to this thing here. Then I get a load of different coordinate derivatives. But the point is, and that's very nice in special relativity, remember that g mu nu is equal to minus 1, 1, 1, 1. And that means that any coordinate derivative always is 0. So once I do any kind of differentiation on this object here, I always get 0. So almost any term I can think of actually vanishes. And that leaves me with a super, super simple equation. So the equation of motion that I get out from this principle in special relativity is exactly this one here. Nothing more, right? And it's kind of maybe obvious. I need a free particle, so I cannot have what corresponds to an external force, so I should get a 0 on the right-hand side. Of course, it must be something related to the 4 vector, not the normal spatial 3 vector, and differentiation must be not with respect not to coordinate time, but with respect to proper time. The only thing that's actually weird now is that it seems that I have an extra component, right? So I have 4 degrees of freedom in this equation, and in the Newtonian equivalent for a free particle, namely this one, I have only 3 components, right? I only have the 3 spatial components. So it seems I have some kind of superfluous degree of freedom. As it turns out, that's not the case, fortunately. So even in special relativity, as it turns out, there are actually only 3 independent quantities. So you can see here that, so for example, let's just make a definition and say that this quantity I call u mu, so that's the 4 velocity. And I can write that out in component language. So normally in special relativity I use, remember, the gamma factor, which is this one here, which in our language is given by this quantity. I can actually write out this u mu to be gamma, gamma v, where this is the normal free velocity of the particle. And actually now I I could also calculate the square of this quantity. What's the length of the 4 velocity? So formally I could write that as a contraction over, or summation over indices here. Really what I'm writing, of course, remember, is T mu nu u mu u nu. But it's the same thing. So this actually I get with the lowered index by acting with the metric on this normal vector here. If I actually write it out in special relativity, then I would get minus u naught squared plus u vector squared. And then I go back up here. I have the components. Then I check. I find a minus 1. Okay? So that means the length of this vector is actually always normalized to minus 1. And that means that if I have the 3 spatial components, the 4th component is given, this one is given in terms of the other 3. So I actually only have 3 degrees of freedom. So that's quite nice. I will not discuss this lowered index version right now, but we'll return to it in just a little while, because it's actually something slightly different from the vector with the upper index. This is called a dual vector, and it's related to this, but it's not equivalent to this. So rather than going in that direction, let's just finish this story for a more general case, not with the metric of special relativity, but with a more general metric of some sort. So I have it here, actually. Remember, the full proper time I could write like this, and then I do all the differentiations. And then, of course, if I have some more general metric, which is time dependent perhaps, or dependent on where I am, then I get non-zero derivatives, and I get a more complicated equation. I no longer get the equation of special relativity. So what I actually do get out is something that looks a little bit nasty. I get out what is known as the geodesic equation. So first, I get the same term as before, not surprisingly. But then I get a different term which encodes information about the nature of the space-time I'm looking at. So for now, I've just written it in terms of this weird-looking symbol, which is either called the Christoffel symbol or the affine connection. And how is that crazy symbol defined? Well, you can see already now that it has 3 indices, which means that it's a rank 3 tensor. So it has 4 by 4 by 4 components. Many of them are identical because it's symmetric under some operations, for example, interchange of alpha and beta, and a few other things too. It must contain coordinate derivatives of the metric, because that's what you get from the variational principle. So we know already that it must in some way contain that. And you can actually write it out. So let me do it. And now I stick to the same notation that I used in the notes. So I have an upper index delta. Just notice that, of course, I can call these anything I want, right? It's just some letter that denotes an index. And then I call it beta and gamma. So let's see. Oops. Like this. And then I get these cyclic derivatives. So let's just write it out. Okay, so that's the full form of this Christoffel symbol. So what you can see is that yes, indeed, it does contain first derivatives of the metric tensor. And that means that, of course, in special relativity, everything like this becomes explicitly zero and that term disappears. But in a more general metric, for example, a time-dependent metric, I will have time derivatives here that I cannot get rid of. One thing that you should notice here is that here I actually have a metric tensor with upper indices. So what the hell is that? Well, that actually is the inverse metric, right? So it's the one where I use the property that, let's just call it delta alpha, it doesn't matter. Let's see, yeah, we can write it like this. Let's call these gamma and beta, then I get like this, sorry. Then I get a Kronecker delta, which is alpha beta, right? So I do one contraction over delta. It's basically just saying in matrix language, this is the inverse matrix of that one. And what I get out, of course, if I multiply a matrix and its inverse, is just that I get the identity matrix out. So I get a 1 if beta is equal to alpha, otherwise I get a 0, right? So this is the inverse metric. That's all it is. So once I have the metric tensor, I can, of course, just do matrix inversion, and then I can find this matrix here, and then I can do the whole calculation. And the magic of general relativity is that this is all there is to it. If I want to know what a particle does, like for example the Earth propagating around the Sun, I assume the Sun is very heavy, so it dominates completely what the space-time looks like in the solar system, then I, through whatever means I have, calculate the metric corresponding to that. Once I have that, then this is the equation of motion for the Earth around the Sun, and that can be done in great detail, and it works like magic. And it just tells us that really in this theory, gravity is no longer a force in the traditional sense. It's actually something that acts only through the metric tensor. It acts only through distortions of space-time. All particles are free particles. Nothing moves under the influence of gravity in the traditional sense. All particles just move in distorted space-times. And that's what looks like Newtonian gravity, for example.